So I actually gave a lot of like a passcode last week, but so currently actually according to like a roster, we have like a more than 100 students in the class, right? But now look at here, yeah, not so many, right? So I mean, obviously like a lot of students are not here, yeah. So well. But my philosophy is I don't take attendance. If you feel like you can study the material by yourself more effectively, I no, that's not a problem with me. Okay. However, okay, if you study by yourself and you don't learn very well, don't bring on me. I mean, it's not my fault, because if you come to a lecture and then you didn't learn well, you don't learn well, then I will try my best to help you. Okay, so that's like if you decide to study by yourself, that's you need to study by yourself. That's your responsibility to study well. Okay, and I, in some sense, I a little bit encourage you to study by yourself, actually, because I think that's an important ability, okay, to have. Like, I mean, that you should train during your college year, okay. 就是说，我觉得大学的时候，你必须要有几科是自己学的啦，要不然的话，等到你将来，你就会觉得说，好像毕业就不想要读东西，这样是不好的哦。Okay, so back to the class. Okay, so today we are going to cover the lecture 2. Okay, it's about asymptotic notation and the recurrences. I believe like this is like 2 chapters in the book, but these 2 chapters mainly deal with mathematics. So let's try to get the math out of the way, because after all, I hope I will still discuss more algorithms, but we do need a math tool, okay, that can help us to talk about the performance of like a different algorithm. Okay, so last week, okay, we actually talked about this one, right? Theta notation, right? So so we are going to deep, into like more notations about these things. Okay. So the first thing is the big O notation. Okay, we usually call this notation as upper bound. Okay, big O as upper bound. Okay, which is actually a very important notation when we discuss algorithms. Okay, so we usually write like Fn, a function is equal to big O g of n if there exists a constant, okay, c, which is a positive number, and n0, I mean, they are positive numbers such that now this equation is satisfied as long as n is greater or equal to n0. So take a closer look. There's an equal sign there. Okay. So this is a big O notation. Okay. Let's give you. Let me give you an example. 2n squared is big O n cubed. Okay. In this particular example, c is 1, n0 is 2. Okay. You can plug in this, f of n and the g of n in this inequality with like these 2 constants to verify if that's correct. But it's relatively easy to make n cubed greater than 2n squared, right? I mean, as long as you can see like n is greater or equal to 2, okay? So, but let me remind you something. First, we usually put functions, okay, at these two places, okay? They represent functions, not values. So you usually don't put value. If you put value, for example, like we also have like a big O1, but that 1 represent a constant function 1, okay? Not like a constant, just a value. No, okay? And also, another thing that you should remember, okay? This is a one-way equality. What do we mean? Okay, we don't say okay, here we have 2n squared equal to big O n cubed, right? Okay, so it looks okay. But if you put it on the opposite direction, this is wrong, okay? This is wrong. To be very frank, very frank, yeah. This big O notation, if you look at the more careful definition, like here, if we use use a more formal definition, what the big O g of n actually represent a set of functions. Okay, so big O g of n equal to all the functions that satisfy this inequality as long as you can find the positive numbers c and n0, okay, that do this job. So obviously, for example, okay, 2n squared equal to big O n cubed. You can imagine, okay, 2n squared also equal to big O n to the power of 4, right? Okay, so so basically, like big O something represent what this thing represent is actually a set, okay, as we indicated here. OK， 我今天讲比较少中文，你们这样 OK 吗？可以吗？还是只有听得懂英文的才会来？啊，都不讲话是听得懂还是听不懂？有人点头。OK， 好 ，OK， 就是说这个 big O G of n 它其实是一个集合哦，它其实是一个 it actually represents a set. So in some sense, okay, as the real the more accurate notation should be 2n squared is an element in this big O n cube. This is the most accurate way, okay, to write this thing. So that's why, okay, we to really like this thing, we call this as like a notation abuse, okay, 就是滥用中文怎么翻译啊？滥用那个这个标示啦。But because everybody do that, so we just accept it's a convention now. Okay, we just use equal sign instead of belong to. Okay, however, okay, this clearly has more problem. Okay, this big O n cube, I mean, on left hand side, this really represents a whole set. So you couldn't, you could assign a whole set into a, a function. So that's like, as I say, it's a one-way equation. I mean, this thing doesn't make sense at all. Okay, so, and you need to remember, this is really like what we really meant in this notation. This equal sign really means belongs to. Okay, really means belongs to. Okay? So the logicians, as I say, or mathematics, mathematicians will say 2n squared should, you should always write like this. But it's convenient to be sloppy, okay? I mean, as I say, everybody do that. So as long as we understand what's really going on, okay, you just need to be careful about this. Okay? So, once you understand that, okay, there are additional, how should I say, like notation abuse about this big O notation. Okay, you can use, that big O notation in a formula which represent an anonymous function in the set. For example, f of n equal to n cubed plus big O n squared. Okay, again, let me remind you, this big O n squared really is really a set of functions. Okay, but so this equation really looks strange. It should look strange, okay, if you are, really careful about the definition of the notation. However, okay, in here, as I say, what we really mean is f of n equal to n cubed plus an anonymous function, okay, h of n, where h of n is an element in big O n squared. Okay, so when we write this, what we really mean is this thing. So again, this is a notation abuse. Okay, just want you guys to understand. Okay, we are not, okay, trying to confuse you. This is just like this type of writing appear, all the time in all different algorithms textbooks. So you have to understand what it really means, and do not get confused, okay? And make sure you understand the real meaning, okay? Based on the definition, okay? And also, like, apologize for some student if you come from, for example, like a mathematics department, you probably don't like it, but that's how computer science, we people in computer science do things. I mean, we just, we are a little bit sloppy in the notation. We focus more on intuition, okay? So as long as we know what we are doing, okay? So, yeah. So big O notation, as I said, it represents upper bound, okay? So it makes no sense to say that, okay, f of n is at least this. At least usually means lower bound, right? For example, like you are at least older than your younger sister. I mean, that usually means, you are older, right? So your younger sister is your lower bound, right, in terms of age, right? So, but big O notation cannot do that. So we have another notation, omega notation. This omega notation, okay, work as a lower bound. Okay, omega g of n equal to f of n, as long as there exist. Okay, I mean, well, of course, this is also a set notation. Okay, I mean, there are so many, many function f. Okay, as long as you can find like a positive constants c and n0, such that this inequality holds for all n greater or equal to n0. By the way, let me remind you again. Okay, this inequality, there's an equal sign. Why do I keep reminding you there's an equal sign? Because we are getting to that point very soon. Okay, so we also can use the notation abuse for this omega notation. Okay, but usually when we discuss things, especially like in this class, most of the time you see like a discussion is about upper bound. Okay, it's not about lower bound, because I mean, when we talk about an algorithm, what you want to guarantee is, I mean, how fast can, for example, how fast can an algorithm, runs? I mean, it really like is bounded by the upper bound, right? So, so for lower bound, it's more like for some more theoretical discussion. So you will see big O more than big omega, to be very frank with you. And this is example. Okay, square root of n. This basically means n to the power of 0.5, right? So it is lower bounded by log n. Okay, and we know the log n is lower bound for any n to the power of something, as long as that something is a positive number. Okay, so in this particular case, we can make c equal to 1, n0 equal to 16. Okay, and of course, like if the power is different, okay, you may need to pick up choose like a different c and n0, but this is always the case. Okay, so n to the power of a positive number must be lower bounded by log n. Okay, log n is you could say log n is a very low order. Okay, of I mean compared to n to the power of something, So we talked about theta notation last week. Okay, at that time we use a definition similar to this. We give like a inequality, okay, to that theta notation. But theta notation, okay, can be because now we understand the big O and big omega. So the theta is pretty much g of n, theta g of n is big O g of n intersect omega g of n. Okay. Remember this, both of these represent, actually this one, all these three represent sets, right? All these three represent sets. So that's why you see like we have this set operation. Okay. Or put it another way, the functions that is in a tight bound with g of n, those functions should belong to both like this set, upper bound and lower bound. Okay, of course, like you will have to choose different. You may need to choose different C and N0, okay, in order to satisfy, for the same function to satisfy, okay, it is upper bound of G of n and it is lower bound of G of n. However, it doesn't change the fact, okay, that function must appear in both sets, okay. Why? Because let me just quickly. L1. Yeah. Let me quickly go to the part that we discussed. Where is it? Running time. Notation. See? We pick C1, C2, right? I mean, if you omit that, C1 and N0 work as a C and N, okay? For this part is more like G of n is a lower bound for f of n, right? So this part, is for like omega notation, and if you omit this part, C2 and N0, okay, work for big O notation. So both are taken care of by this one equation, okay. But yeah, so that's why tight bound, or like we say some people say tight bound, some people say approximate, asymptotic bound. Some people say some people call it differently, but depending on the textbook. But basically, theta notation, okay, is basically like the intersection of like big O and big omega. Okay, go back to here. So remember, I keep telling you, okay, in the inequality, there's an equal sign there, right? So why do I need to keep emphasizing that? It is because, okay, other than big O and the big omega, we also have small o and the small omega. Okay, for small o and the small omega, the definition looks so similar to big O and the big omega. The only difference is that we no longer have equal sign here. For example, this one is for small o. So originally in the big O notation, there's an equal sign here. Now with the small o, there's no equal sign here. Okay, so the same thing, 2n cubed and 2n squared and the n cubed. I mean, not only is n cubed is a big O, is the upper bound for 2n squared. Okay, it is also like big small o, okay, for 2n squared, because obviously this order is higher, obviously, right? So this, you can easily choose like a N0 and a C to make this case, okay, to make this equation, this inequality like hold, okay? So and this is for the omega, okay, small omega, same thing. That in the equality, like the equal part, equal sign is disappear. Okay, so for similar reason, okay, square root of n equal to small omega log n. Okay, but as I said, like again, you may need to pick different n0. and C. Okay, so basically, okay, the big O and and small o, big O and the big omega is, I mean, when we discuss the order, it's kind of like a smaller or equal, and or larger or equal, So I mean, when we discuss orders, but the small o notation and the small omega notation is like a smaller than and a larger than. When we discuss, like when we use them to discuss like order, so you wouldn't be able to find something that is what should I say? The intersection of small o g of n and small omega g of n, okay, is empty, okay, because it's inequality, right? I mean, we know, like for example, like it makes sense to write like A smaller or equal to B smaller or equal to A, right? It is okay. You have this inequality, right? Right? I mean, you just make like a, B equal to A. That's, I mean, it is fine, right? But you do not have this doesn't hold, right? You couldn't have anything that satisfies this, right? So this one is kind of like a big O notation, okay, and the big omega. This part is like a small o and small omega, okay? So we are done with like those like notations, okay? And before we dip into like a recurrence, the first thing, there are many tools out there, especially in your calculus, okay, that can help you to calculate like those big O, small O. Yeah, I think I'm there's something I missed. Where is it? Yeah, I remember there's a. Okay, never mind. Okay, so although we talk about a lot of these inequalities, okay, but for example, given a function, let me go back to big O. Given a function, okay, if you want to find the big O, okay, say you put the first thing, if your function, okay, if this is f of n equal to something plus da 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 da, okay, if you can put these terms in order of the order for each terms, where this one the first thing is the highest order, the others represent like smaller orders. Then, okay, when you want to find a big O of Fn, you can drop them. And also, if they are you can again drop the leading constants. Okay, when we discuss like a big O notation, okay, I mean it is much more convenient. You don't have to use the whole complicated like a formula, the whole thing. Qualities, because those you know, lower order terms doesn't change the big O, doesn't change the upper bound. Okay, it will just make the discussion, okay, the formal discussion complicated. Okay, so in computer science, as I previous told you guys, we are a little bit slight.